Welcome back, ladies and gentlemen. Thank you for returning, participating, and hopefully enjoying this phenomenal series by Anatoly Fomenko, Fiction or Science. What is this thing we call history? We are on the 7th reading, Chapter 2, Astronomical Datings, the Strange Leap of Parameter D in the Theory of Lunar Motion. Nowadays, we have special calculation tables, the so-called canons, whose compilation was based on the theory of lunar motion. They contain the date of each eclipse, the area to be covered by the lunar shadow, the phase, etc. See the famous astronomical canon of Ginzel, for instance. If an ancient text describes some eclipse in enough detail, we can determine what characteristics of the eclipse had been observed: the phase, the geographical area that the shadow passes over, etc. The comparison of these characteristics to the referential ones contained in the tables may give a concurrence with an eclipse possessing similar characteristics. If this proves a success, we can date the eclipse. However, it may turn out that several eclipses from the astronomical canon fit the description. In this case, the dating is uncertain. All the eclipses described in the quote, ancient, unquote, and medieval sources have been dated by the following method to some extent, at least. Nowadays, the datings of the ancient eclipses are occasionally used in astronomical research. For instance, the theory of lunar motion has the notion of the so-called parameter D, the second derivative of lunar elongation that characterizes acceleration. Let us remind the reader of the definition of elongation. Figure 2.1. Figure 2.1 shows the solar orbit of the Earth and the telluric orbit of the Moon. The angle between the vectors ES and EM is called lunar elongation D, the angle between the lines of sight drawn from the Earth to the Sun and the Moon. Apparently, it is time-dependent. An example of the elongation of Venus can be seen in the picture on the right. Maximal elongation is the angle where the line of sight, as drawn from Earth to Venus, touches the orbit of Venus. One has to note that the orbit in Figure 2.1 are shown as circular while being elliptic in reality. However, since the eccentricity is low here, the ellipses are schematically drawn as circles. Some computational problems related to astronomy require the knowledge of lunar acceleration as it had been in the past. The problem of calculating parameter D over a large time interval as a time function was discussed by the Royal Society of London and the British Academy of Sciences in 1972. The calculation of the parameter D was based on the following scheme. The equation parameters of lunar motion, including D, are taken with their modern values and then varied in such a way that the theoretically calculated characteristics of ancient eclipses coincide with the ones given for dated eclipses in ancient documents. Parameter D is ignored for the calculation of actual eclipse dates, since the latter are a rougher parameter whose calculation does not require the exact knowledge of lunar acceleration. Alterations in lunar acceleration affect secondary characteristics of the eclipse, such as the shadow track left by the moon on the surface of the Earth, which may be moved sideways a little. The time dependence of D was first calculated by the eminent American astronomer Robert Newton. According to him, parameter D can be defined well by the abundant information about the dates scattered over the interval from 700 BC until the present day. Newton calculated 12 possible values of parameter D, having based them on 370 ancient eclipse descriptions. Since Newton trusted Scaligean chronology completely, it is little wonder that he took the eclipse dates from Scaligean chronological tables. The results of R. Newton, combined with the results obtained by Martin, who has processed about 2,000 telescope observations of the moon from the period of 1627 to 1860, 26 values altogether, have made it possible to draw an experimental time dependency curve for D. According to R. Newton, the most stunning fact is the drastic drop in D that begins with 700 and continues until about 1300. This drop implies the existence of a square wave in the oscillating value of D, such changes in the behavior of D, and such rates of these changes cannot be explained by modern geophysical theorists. Robert Newton wrote an entire monograph titled Astronomical Evidence concerning non-gravitational forces in the Earth-Moon system. That was concerned with trying to prove this mysterious gap in the behavior of D, which manifested as a leap by an entire numeric order. One has to note that these mysterious non-gravitational forces failed to manifest in any other way at all. Having studied the graph that was drawn as a result of these calculations, R. Newton had to mark that between the years, the value of D remains the lowest as compared to the ones that have been observed for any other moment during the last 1,000 years. Newton proceeds to tell us that these estimations combined with modern data tell one that D may possess amazingly large values, and that it has been subject to drastic and sudden fluctuations over the last 2,000 years, to such an extent that its value became inverted around 800 AD. A quick summary. The D value drops suddenly, and this leap by an entire order begins in the alleged 5th century AD. Beginning with the 6th century and on, the values of parameter D become more or less constant and close to its modern value. In the interval between the alleged 5th and 11th centuries AD, one finds D values to be in complete disarray. This strange fact has a natural explanation within the paradigm of the new chronology. For those of you that are just listening, think of D if you want to get a mental picture of what D is, how they're studying it. Think of a protractor that is at a 120-degree angle. Or better yet, you could think of a clock with the large hand at 11 and the small hand at 3. So say 2:55. And what they're measuring is if you have that clock and you drew a circle right at the point where those hands are meeting on the bottom down there, that angle, if you drew a little half circle between the big hand at 11 and the small hand at 3, that little angle right there, that 120-degree little half circle angle would be D. I hope that helps for those that are just listening. Are the ancient and medieval eclipses dated correctly? 2.1. Some astronomical data. Let us give a brief digest of the information that shall ensure a better understanding of the current chapter. When the moon gets into the cone of telluric shadow, one can observe a lunar eclipse on Earth, more specifically on its nocturnal hemisphere, the one that faces the moon. And if you are a dummy like me and had to look up the word telluric, then, or if you lied to yourself and you said you knew what that word was like me, allow me to look it up for you. Telluric means from the earth, an energy of the earth. On a fun side note, a telluric current is a current of the earth. It is an electric current which moves underground or through the sea. Telluric currents result from both natural causes and human activity, and the discrete currents interact in a complete complex pattern. The currents are extremely low frequency and travel over large areas at or near the surface of the earth. I think that's something Tesla was tapping into in his later days. Let us get back to the book. A lunar eclipse can be observed from any point of the Earth's nocturnal hemisphere. An eclipse does not last longer than 3 hours and is only possible during a full moon. However, due to the irregularity of lunar motion, it does not happen every time the moon is full. The repetition of lunar eclipses is roughly and approximately periodic and confronts to the so-called Saros cycle. A Saros period equals about 18 years. 28 lunar eclipses occur over this time. So one can find an eclipse that falls over virtually every given year. A Saros is easily determined over 50 to 60 years of systematic observation, and might have already been known at the dawn of astronomy. The prediction of lunar eclipses based on the Saros cycle is nevertheless somewhat uncertain, not only due to the imprecision of the Saros cycle, but also because of the fact that the eclipse might occur when the hemisphere where the observer is located is illuminated by sunlight, which renders the moon invisible. A solar eclipse occurs when the observer gets into the cone of the lunar shadow. If the solar disk is completely covered by the moon, the place where the eclipse can be observed becomes darkened to the extent of making the stars visible. This is a full eclipse, whose duration does not exceed 8 minutes. In the equatorial zone and 6 in moderate latitudes, the lunar shadow moves across the surface of the Earth at the speed of about 110 meters per second, forming a narrow line. The width of this line does not exceed 4 degrees. The track of the umbral shadow is bordered by stripes of the penumbral shadow, whose width is counted from the center of the umbral shadow, comprises about 30 degrees in moderate latitudes and about 15 degrees near the equator. The observer in the penumbral shadow only sees a partial covering of the solar disk by the moon, a partial eclipse. The maximal degree of the covering of the solar disk by the lunar shadow is called the depth, or the phase of the eclipse. The estimations of the phase are usually expressed by the B value, that is calculated by the formula B equals 12H, H being the ratio between the shadow covered part of the solar diameter and the entirety of the latter. Hence, a total eclipse of the sun will have a phase value of 12. A solar eclipse becomes visible as a darkening of the solar disk, starting with the phase values of 3 to 4 inches. The lunar eclipse phases are calculated differently, namely, another item that is proportional to the duration of the eclipse if the latter is more than full is added to the phase value of 12 inches. Thus, the phase value of a lunar eclipse might reach up to 22.7 inches. In cases of solar eclipses, there may be situations when the cone of the moon's umbral shadow does not reach the Earth. In this case, an annular solar eclipse is possible. When no stars are visible, as is the case with all partial solar eclipses, a solar eclipse is only possible when the moon is new. However, not every new moon is marked by a solar eclipse, since the Earth may slip past the cone of the lunar shadow due to the incline of the lunar orbit towards the ecliptic or the plane of the telluric orbit. This is why there are only 2 to 7 solar eclipses happening every year. Every geographical area of the Earth gets an eclipse with a minimal phase value of 6 inches in the span of 10 to 20 years from any date. Predicting solar eclipses is a truly formidable task due to the complexity of the lunar motion that is defined by a large number of external factors. One may attempt to predict solar eclipses by the Saros cycle that includes about 43 solar eclipses, 15 of them being partial, 14 annular, 2 belonging to the category of the so-called total annular, and 12 total. However, the eclipses from the Saros cycle can occur in different areas of the Earth, and so a prediction for a given location is true in one case out of 400 in general. That is to say, the probability of a correct prediction based on the Saros cycle equals 1 in 400. In theory, the so-called triple Saros, whose duration is 24 years, should be more precise. However, the probability that it may give a correct prediction equals about 1 in 100. So it is of little practical utility. From the astronomical point of view, the empirical triple Saros can only be discovered as a result of long-time solar eclipse observations. Due to the low recurrence rate of the eclipses separated by the triple Saros, let alone the problems of mathematical processing of the empirical data necessary for the calculation of an undefined recurrence rate, any such discovery would imply a well-developed system of natural sciences. A more or less certain prediction of solar eclipses is apparently only made possible by the existence of a sufficiently advanced theory of lunar motion that would at least account for the principal irregularities of the latter. Thus, the prediction of solar eclipses remained a de facto impossibility 100 years after Copernicus. We should thus treat the eclipse prediction reports preceding the 16th to 17th centuries with the utmost caution, or even suspicion. The discovery of an interesting effect in unprejudiced astronomical dating shifts the dates of the ancient eclipses to the Middle Ages. Dealing with certain celestial mechanics issues in the 1970s, the author of the current book discovered the possibility of a link between the alleged gap in the value of D and the results of N.A. Morozov's research concerning the datings of ancient eclipses. A study of the issue and a new calculation of parameter D attains an altogether different quality, namely, one sees the complete elimination of the mysterious leap parameter D. Parameter D appears to be subject to minute fluctuations around one permanent value, coinciding with the current value of this parameter. All of this can be summed up as follows. The previous calculation of the parameter D was based on the dates of ancient eclipses used in the consensual chronology of Scaliger-Petavius. All the astronomers' attempts to explain the strange gap in D did not get anywhere near the issue of the correctness of datings considered ancient and early medieval nowadays. In other words, in how far the parameters of the eclipse described in the chronicle correspond with the calculated parameters of the real eclipse that Scaligerian chronology suggests to be described in the chronicle in question. The following method of independent astronomical dating was proposed. Obtaining all of the characteristics described in the chronicle, such as the phase, the time, geographical observation, location, etc., and copying all of the eclipse dates fitting these characteristics from the reference tables mechanically, N.A. Morozov discovered that the astronomers have been under the pressure of Scaligerian chronology, and so only considered the dates that Scaligerian chronology had already ascribed to the eclipse in question and the events related thereto. As a result, in many cases, astronomers failed to find eclipses corresponding to the chronicle description in the required century and had to resort to approximations. Without the merest thought of questioning Scaligerian chronology and indicating eclipses that would fit the chronicle description partially. Having revised the datings of the eclipses considered ancient, Morozov found that the reports of these events fall into two categories: brief and nebulous accounts with no details given. In many cases, it is altogether unclear whether the event described is an eclipse at all. The astronomical dating in this category either has no meaning whatsoever or gives so many possible solutions that they can basically fit any historical epoch at all. Exhaustive, detailed reports. 2. Exhaustive, detailed reports. The astronomical solution for those is often singular, or there are 2 or 3 solutions at most. Apparently, all the eclipses which detailed descriptions falling into the period between 1000 BC and 500 AD get independent astronomical datings that differ significantly from the ones offered by Scaligerian chronology and belong to a much later epoch, namely the interval between 500 and 1700 AD. Being of the opinion that Scaliger chronology was correct about the interval 500 to 1800 AD, for the most part, Morozov did not analyze the medieval eclipses of 500 to 1700 AD, assuming that no contradictions would be found there. Let us dwell on this for a short while. Morozov didn't possess the sheer deliberation needed for the realization that Scaligerian chronology had been erroneous up until the epoch of the 11th through 13th century. He stopped with the 6th century AD, assuming more recent chronology to be correct in the form offered by Scaliger and Petavius. His erroneous presupposition naturally affected the analysis of the ancient eclipses. We see today that Morozov's analysis was not completely objective, since he had obviously been reluctant to alter the post-6th century chronology. This isn't hard to understand, as the transition from the artificially extended Scaligerian chronology spanning millennia to a much shorter one beginning with the 6th century AD looked absurd even to Morozov. For instance, Morozov discusses one of the eclipses that is today ascribed to the 5th century, being of the opinion that its Scaligeриan dating is confirmed. However, it becomes obvious that no confirmation of the Scaligeриan chronology could have possibly taken place. The description of the eclipse is quite nebulous, and the use of comets for dating purposes is impossible due to reasons that shall be related in the chapter of Chron 5, where we consider comet lists specifically. Being certain that Scaligeриan history was following the correct chronology ever since the 5th century AD. Morozov was inconsistent in his analysis of post-5th century eclipses. Had he encountered an equally nebulous description referring to the pre-4th century eclipse, he would have justly considered it a description that cannot be proved astronomically. Morozov made a similar mistake in his descriptions of other eclipses dated to the alleged 5th and 6th century. He treated them a lot more benevolently. Than their pre-4th century precursors. The eclipses of the 6th through 9th century were not checked by Morozov at all, since he had believed the Scaligeриan datings to have been satisfactory. Unlike Morozov, we have continued with the critical research, having covered the post-5th century period up until the 17th century, and discovered that Morozov should not have stopped with the 4th and 5th century. The datings of the eclipse descriptions that are ascribed nowadays to the 10th through 13th centuries contradict astronomy to just as great an extent as those preceding the 4th century. In cases where there's a concurrence of sorts, one almost always discovers that the eclipses have been calculated a posteriori, that is, affixed to a certain point in the past by the medieval chronologers of the 16th through 17th century in order to confirm Scaligeриan chronology, whose nascence occurred around that time. Having calculated the dates for certain lunar eclipses of the past, Scaligeриan chronologers included them in the ancient chronicles that they were creating in order to give, quote, solid proof, unquote, to the false chronology. It is, of course, possible that the odd occasional veracious description of the 6th through 13th century eclipses would reach the chronologists of the 16th through 17th century. However, it would surely have to pass the filter of the Scaligeриan version and be brought into accordance with the correct dates. Thus, continuing the research that began, the author of this book conducted an analysis of other medieval eclipses in the interval between 400 and 1600 AD. It turned out that the transfer effect affecting the ancient eclipses, as described, also applies to those usually dated to 400 900 AD. This either means that there are many possible astronomical solutions which make the dating uncertain, or there are just one or two, in which case they all fall in the interval between 900 and 1700 AD, only starting with approximately 1000 AD and not 400 AD, according to Morozov. Does the Scaligeриan dating begin to concur with the results of Morozov's method satisfactorily enough, becoming more or less certain by as late a date as 1300? Let us give a few extremely representative examples demonstrating how the ancient eclipses and the chronicles that describe them become a great deal younger.